There is a thought experiment that cosmologists rarely share in public settings, not because it requires advanced mathematics to appreciate, but because the answer is genuinely unsettling in a way that polished lecture halls and conference presentations tend to smooth over. The experiment is simple to state. Imagine you could leave. Imagine you could step outside of everything familiar, outside the thin atmosphere of this planet, outside the gravity well of our sun, outside the spiral arms of the Milky Way, outside the gravitational embrace of our local group of galaxies, and simply keep going. Not for a few thousand light years, not for a few million, not even for the tens of millions of light years that separate our galaxy from the nearest large cluster. But for 1 billion light years, 1 billion. Imagine you travelled that incomprehensible distance and then, at last, you stopped. You turned around. You looked back toward the direction of home. What would you see? Most people, even those with a genuine interest in astronomy, even those who have read books about cosmology and watched documentaries about deep space and spent evenings lying on their backs in fields identifying the constellations, give an answer that is not quite right. They imagine a grand panoramic view. They picture our galaxy hanging in the remote distance like a glittering island, a flat spiral of light suspended against a dark background, recognizable even from that distance by its distinctive shape, surrounded by other island galaxies scattered across a comprehensible sea of space. They imagine something like the famous Hubble Deep Field photographs, galaxies upon galaxies receding into the distance, the whole scene majestic and ordered, and ultimately legible. They imagine, in short, a universe that looks like the one they have been shown in textbooks and planetarium shows. That image is not wrong. But it is incomplete in a way that changes everything about how the universe must be understood. Because at 1 billion light years, the universe does not simply look larger than what you have imagined. It reveals an architecture that is invisible from any closer vantage point. An architecture built on scales so vast that our nearest cosmic neighborhood, everything within 100 million light years of Earth, is too small a sample to make it visible. The structures you encounter on that journey outward, the walls and voids and filaments of matter that define the universe at its largest observable scales, follow organizational principles that were not properly understood until the closing decades of the 20th century. The forces acting on space itself at those distances are stranger and more counterintuitive than anything in our everyday experience of physics, and the philosophical implications of what you would observe, looking back from that distance toward the single point that contains everything human civilization has ever known, done, or dreamed, are the kind that cosmologists tend to discuss quietly and carefully, because they press on questions that science alone cannot fully answer. By the time this journey is finished, you will understand why 1 billion light years is not simply a very large number. It is a threshold. It is the scale at which the universe's true skeleton becomes visible, the scale at which the individual stories of galaxies give way to the single, vast story of structure itself. It is the distance at which the expansion of space stops being an abstract, textbook fact and becomes something you can feel pressing against you in every direction. And there is one discovery, something confirmed only within the last few decades by observations that initially seemed impossible. Something that remains one of the most profound and disturbing facts in all of science that will become fully comprehensible only from this distance. That discovery is not merely about what the universe contains. It is about what the universe is made of and what it is doing and where it is going, and when you understand it fully, The universe you inhabit will never look quite the same again. We are going to travel that billion light years together. We are going to stop at every meaningful threshold along the way, at every scale where the universe reveals something new about its character, and we are going to understand what is actually happening, physically and geometrically and philosophically, at each stage. We will build the journey, one order of magnitude at a time, so that by the time we arrive at our destination, the distance will feel earned rather than simply stated. And when we finally stop and turn around, you will understand not just how far we have come, but what it means to have come that far. What it means that light from this moment on Earth will take 1 billion years to reach the point where you are standing, which means the Earth that emitted those photons, the Earth of 1 billion years ago, was a world without animals, without forests, without anything that would recognize itself in the mirror of your face. The journey is not only through space, it is through time. And the two, as Einstein showed, were never really separate to begin with. If this kind of exploration is something you find worthwhile, consider subscribing before we begin. This channel reaches curious people because curious people share it, and every one of them makes the next journey possible. Now, let us go. The first thing that needs to be established before we take a single step is what we actually mean when we say 1 billion light years, because this phrase is one of those measurements that gets repeated so often in popular science that it begins to feel familiar, almost comfortable. And that familiarity is a lie. There is nothing comfortable about this number. It defies every intuition the human nervous system possesses, and the only honest way to approach it is to build toward it from the ground up, one step at a time, so that each multiplication of scale lands with its full weight rather than sliding past unnoticed. A light year is the distance that light travels in one calendar year. Light moves at approximately 186,000 miles per second, or roughly 300,000 kilometers per second. This is the fastest speed that anything in the universe can travel. At this speed, light can circle the entire Earth 7.5 times in a single second. In 1 year, light covers approximately 5.9 trillion miles. Write that out in full, 5,900 billion miles. That is 1 light year. It is the distance from Earth to the Sun, those 93 million miles we think of as a vast gulf, multiplied by 63,000. It is the distance light covers in the time between one birthday and the next. Now, multiply it by 1 billion. The number you get is approximately 5.9 times 10 to the 21st miles. In spoken words, that is 5.9 sextillion miles. To place that in any kind of human frame, if you tried to drive that distance in a car at 60 miles per hour, stopping for nothing, eating and sleeping behind the wheel, the journey would take roughly 11 quadrillion years. The universe itself, at 13.8 billion years old, would need to live out its entire current lifespan nearly 800 more times to give you enough driving hours to complete the trip. Your car would have no fuel, no road, no destination, and no driver by the end of the first billion years, but the distance itself would continue regardless, indifferent to all of that. These comparisons are not offered as entertainment, they are necessary, because the scale of this journey defines the nature of everything we will observe along the way. When we say the universe has a structure that only becomes visible at 1 billion light years, we are saying that the organizing principle of the cosmos operates at a scale that is, in every physical sense, permanently unreachable by any vehicle humanity has ever conceived or could realistically conceive. We can see this structure. We can map it with extraordinary precision. We can understand the physics that built it. But we will never visit it the way Columbus visited the Americas or Armstrong visited the moon. The journey we are taking exists in the only medium capable of spanning this distance without a ship: understanding. So let us build that understanding from the first light year outward. Begin with the distance from here to the moon, 239,000 miles. Light crosses that distance in approximately 1.3 seconds. When you look up at the moon on a clear night, you are seeing it as it was 1.3 seconds ago. That delay is so small it has no meaningful consequence for anything you do, but it is real. The moon you see in the sky is not the moon as it currently exists in the universe. It is an image from the recent past, preserved in the light that left its surface 1.3 seconds before reaching your eyes. Every observation is an act of looking backward in time. The further the object, the further back in time you are looking. This is the first principle of cosmological travel, and it will press more heavily on us with every order of magnitude we add to our distance. From the moon to the sun is 93 million miles. Light takes approximately 8 minutes to cross that gap. The sunlight warming your skin on a summer afternoon left the surface of the sun 8 minutes ago. The sun you see in the sky is the sun as it was 8 minutes in the past. If the sun were to vanish at this precise moment, you would not know for 8 full minutes. For 8 more minutes, the sky would remain blue. Shadows would continue to fall. Plants would continue their photosynthesis, and nothing would alert you to the fact that the star your planet orbits had ceased to exist. Then the light would stop arriving and the darkness would come, without warning, 8 minutes after the event that caused it. This delay between event and observation is not a minor technical footnote. It is a fundamental structural feature of a universe governed by the speed of light, and it scales with every order of magnitude of distance we add. At 1 billion light-years, the delay is 1 billion years. Events that happened 1 billion years ago are, from that distance, events that are happening right now, as far as our observations are concerned. The past and the present become, at cosmic scales, genuinely indistinguishable. To observe is always to remember, never to witness. Push outward from the sun. The outer boundary of the solar system. The region called the heliopause, where the solar wind finally loses its battle against the interstellar medium flowing between the stars, lies at roughly 120 astronomical units from the Sun. 1 astronomical unit, the average Earth-Sun distance, is those 93 million miles. At 120 astronomical units, light takes approximately 16.5 hours to make the journey from the Sun. 2 spacecraft have crossed this threshold. Voyager 1, launched in September of 1977, crossed the heliopause in August of 2012, 35 years after leaving Earth, traveling at approximately 35,000 miles per hour. Voyager 1 is currently the most distant human-made object in the universe. At Voyager's speed, crossing 1 full light-year would take roughly 17,000 years. To cross 1 billion light-years at that speed would take approximately 17 trillion years, which is more than 1,000 times the current age of the universe. This is not a limitation of this particular spacecraft. It is a statement about the fundamental relationship between the speed of light, the speed of matter, and the architecture of the cosmos. The speed of light is not just fast, it is the cosmic speed limit, and everything with mass falls infinitely short of it. The universe is structured at scales that, by the physical laws that govern it, can only be crossed by light and by the ideas carried in minds that can think faster than any spacecraft. Beyond the heliopause, the true interstellar medium begins. It is not empty in any absolute sense. It contains gas, primarily hydrogen, at densities of roughly 1 atom per cubic centimetre. Compare this to the air at sea level, which contains approximately 2.7 times 10 to the 19th molecules per cubic centimetre, and you begin to understand the character of interstellar space. For every molecule of air in a sugar cube-sized volume at sea level, there is 1 hydrogen atom in a cubic centimetre of interstellar space. The difference spans more than 19 orders of magnitude. Interstellar space is, for all practical purposes, the most perfect vacuum that exists in nature, and we must travel through hundreds of billions of light-years of it before encountering anything we would recognize as densely packed matter. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. It is a small, dim red dwarf, part of a triple star system that also includes 2 larger, Sun-like stars orbiting each other in a gravitational dance that takes roughly 80 years to complete. At Voyager's speed, reaching Proxima would take approximately 73,000 years. Around Proxima, astronomers have confirmed at least 2 planetary candidates, including one in the habitable zone where the temperature might, under the right atmospheric conditions, permit liquid water on a surface. We note this possibility and move on. We are not stopping for individual planetary systems. We have architecture to find. 100 light-years from Earth, we are surrounded by a sphere containing a few hundred stars. The majority of them are red dwarfs, smaller and cooler and dimmer than the Sun, burning their nuclear fuel so slowly and so efficiently that many of them will continue shining for trillions of years after the Sun has exhausted its own supply. Red dwarfs are the tortoises of stellar evolution, unremarkable and overlooked, but they will outlast every other kind of star in the galaxy by an enormous margin. Within our 100 light-year sphere, we also find the stars that human cultures named and wove into mythology. The stars of Orion, whose light left home around the time of early medieval Europe. The stars of the Southern Cross, familiar to every seafaring civilization of the Southern Hemisphere. These ancient travellers, photons that predate the printing press and the fall of Rome, reach human eyes after crossing a century of vacuum that contains almost nothing, and we call them beautiful. 1,000 light-years out, the sphere contains tens of thousands of stars, and the local structure of the Milky Way's Orion arm becomes faintly visible in the distribution of star-forming regions, gas clouds, and young blue stars tracing the curve of a spiral arm that we inhabit. The Milky Way itself spans approximately 100,000 light-years from edge to edge and perhaps 1,000 light-years in thickness at our location in its outer regions. It contains, by current estimates, somewhere between 100 billion and 400 billion stars. The uncertainty in that range is not a sign of carelessness. It reflects the genuine difficulty of counting the members of a structure you are embedded inside, obscured from a clear view by layers of dust and gas that block the light from hundreds of billions of stars in the galaxy's more distant regions. At 100,000 light-years, we have crossed the full diameter of the Milky Way. Everything you have ever seen with the naked eye, every star, every constellation, every streak of light across the night sky that a child has ever pointed at and asked about, fits inside this disk. The entire accumulated starlight of human history is contained within a structure that is, at our current scale of travel, barely a step. We have covered 100,000th of our total journey. The remaining 999,900,000 light-years wait ahead. 2.5 million light-years from Earth, we arrive at Andromeda. The Andromeda Galaxy, catalogued as Messier 31 by the French astronomer Charles Messier in 1764, is the most distant object visible to the unaided human eye. On a night dark enough and clear enough, it appears as a faint, elongated smudge in the constellation Andromeda, roughly 6 times the apparent width of the full moon, but so much dimmer that most people never notice it, without being told exactly where to look. That smudge is the combined light of approximately 1 trillion stars, making Andromeda somewhat more massive than the Milky Way by most current estimates. Andromeda is approaching us. It is currently closing the gap between our galaxies at approximately 110 kilometers per second, meaning that every second brings it nearly 70 miles closer to the Milky Way than it was the second before. In approximately 4.5 billion years, the two galaxies will begin to overlap and merge. This eventual collision is often described in dramatic terms, as a catastrophe, as the death of two galaxies, as a cosmic collision of unimaginable violence. But the reality, while spectacular by astronomical standards, is far quieter than that language suggests. When galaxies merge, the individual stars within them almost never physically collide. The reason is the same reason interstellar space is so nearly empty. The distances between stars are so enormous relative to the sizes of the stars themselves that two galaxies can interpenetrate each other like two swarms of fireflies passing through the same space, with the individual insects never touching. The Sun's nearest neighbour is 4 light-years away. The Sun itself is less than 150 million kilometres across. At the scale of the galaxy, stars are like grains of sand, separated by miles of open countryside. Two galaxies merging is not a collision of individual stars. It is a gravitational reorganization of their collective mass, accompanied by vast, triggered episodes of star formation as gas clouds are compressed by the interaction and by the slow, tidal distortion of both systems as they draw out long streamers of stars into space before eventually settling into a single merged galaxy. The Sun, if it still exists by then, which depends on whether it survives the slow swelling of our own aging star over the coming billions of years, will likely find itself relocated to a new position in the merged galaxy without having come anywhere near another individual star during the entire process. From Andromeda, we move outward through the local group, the gravitationally bound family of galaxies to which the Milky Way belongs. The local group spans roughly 10 million light-years in diameter and contains approximately 80 known members, though the count continues to grow as surveys improve their sensitivity to the very faintest dwarf galaxies. Most of its members are small, dim, irregularly shaped collections of a few billion stars or fewer, satellite galaxies orbiting the two dominant spirals the way moons orbit planets. The Milky Way itself hosts a collection of satellite galaxies, the most prominent of which are the Magellanic Clouds, visible from the southern hemisphere as detached patches of luminosity alongside the main band of the Milky Way. The large Magellanic Cloud contains roughly 30 billion stars. The small Magellanic Cloud contains perhaps 3 billion. Both are being slowly disrupted by the Milky Way's gravity. their outermost stars pulled away into tidal streams that arc across millions of light years of sky, the galaxy slowly swallowing its smaller companions over cosmic time. At 54 million light-years, we reach the Virgo cluster. This is a genuinely large structure containing more than 1,300 confirmed galaxies within a volume roughly 15 million light-years across, all of them bound together by their mutual gravity into a gravitational knot that will persist for tens of billions of years. The Virgo cluster is anchored at its core by several enormous elliptical galaxies, the largest and most dramatic of which is the galaxy designated Messier 87. This galaxy is extraordinary by almost any measure. It contains roughly 1 trillion stars. At its center sits a supermassive black hole with a mass 6.5 billion times that of the Sun, making it one of the most massive black holes ever directly confirmed. From the vicinity of this black hole, a jet of magnetically confined plasma shoots outward into space for roughly 5,000 light-years, a torch of particles moving at close to the speed of light, visible across enormous distances to any telescope sensitive to the right frequencies of radiation. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole in history, constructed from data collected simultaneously by radio telescopes on multiple continents working together as a single Earth-sized instrument. The image showed the black hole at the center of Messier 87. A dark circular shadow surrounded by a bright asymmetric ring of glowing gas, bent and focused by the extreme curvature of space-time around the black hole's boundary. The image was exactly what general relativity predicted. Every detail of its shape and brightness distribution was consistent with the equations Einstein published in 1915. That a theory developed from thought experiments and pencil calculations on paper in the early 20th century should describe with such precision an object 6.5 billion times the mass of the Sun, 55 million light-years away, is among the most striking demonstrations of the power of mathematical physics that science has ever produced. The Virgo cluster does not exist in isolation. It is the gravitational heart of a much larger structure called the Virgo supercluster, which in turn is now understood to be a lobe of the even larger structure called Laniakea. First properly defined and described in a landmark 2014 study by a team led by the astronomer Brent Tully, Laniakea is the gravitational watershed that encompasses the Milky Way, the Virgo cluster, and thousands of other galaxy groups and clusters across a volume roughly 520 million light-years in diameter. The name comes from the Hawaiian language and means immeasurable heaven, a name chosen to honor the tradition of Pacific Islanders who navigated the open ocean using an understanding of celestial patterns that was, in its own way, a form of large-scale spatial reasoning about the universe. The key insight in the Laniakea study was that superclusters should be defined not by simple proximity, but by gravitational flow. The team mapped the motions of thousands of galaxies throughout the local universe, tracing the streams of matter falling under gravity toward dense regions and identifying the watershed boundaries where gravitational flow switches from moving toward one concentration to moving toward another. These boundaries, analogous to the drainage divides between river basins on Earth, define the true extent of each supercluster. By this definition, Laniakea contains the mass of approximately 100 million billion solar masses, organized into thousands of individual galaxies that are all, in the long run, gravitationally part of the same cosmic neighborhood. We stand at the edge of Laniakea now. Behind us is the entire history of astronomical discovery, everything humans have ever named and measured and catalogued within our gravitational home. Ahead are 950 million more light-years of universe, and at the edge of that distance, something that will require everything we have learned so far to properly understand. The skeleton of the universe does not reveal itself from inside any single supercluster. You have to step back far enough to see the bones beneath the skin. And we are just now stepping back far enough. The structure that becomes visible at scales of hundreds of millions of light years is called the cosmic web, and it deserves that name. It is not a metaphor. It is the most accurate description of what the universe actually looks like at its largest observable scales, a three-dimensional network of filaments and sheets and dense nodes threaded through enormous empty regions, forming a pattern that repeats with statistical regularity across the entire observable universe. It is the universe's fundamental architecture, and it was built not by any force that acts on small scales, but by the accumulated work of gravity over 13.8 billion years, operating on density differences that were themselves the product of quantum fluctuations in the first tiny fraction of a second after the Big Bang. To understand how the cosmic web came to exist requires going back to the very beginning, to a moment so early in the universe's history that the concepts of space and time themselves were only just becoming meaningful. In the first fractions of a second after the Big Bang, the universe was an extraordinarily hot, dense plasma, a seething mixture of fundamental particles, radiation, and energy in conditions so extreme that even the simplest atomic nuclei could not yet hold themselves together. The universe at this moment was almost perfectly uniform, smooth to a degree that everyday language struggles to convey, but not perfectly smooth. Quantum mechanics, the theory that governs the behavior of matter and energy at the smallest scales, predicts and requires that the early universe contained tiny, random fluctuations in density. These fluctuations were not imposed from outside. They arose from the fundamental probabilistic nature of quantum processes, the same nature that means an electron does not have a precise location until it is measured, the same nature that underlies every transistor in every computer ever built. In the early universe, these quantum fluctuations manifested as regions that were infinitesimally denser than the average, surrounded by regions that were infinitesimally less dense. The amplitude of these initial fluctuations, the size of the density variations, was roughly 1 part in 100,000, meaning the densest regions had only slightly more than average amounts of matter, a difference so small that placed side by side, you could not distinguish them by eye or by any ordinary means. Gravity is patient. It does not care how small a density difference is, it only cares that a difference exists. The slightly denser regions attracted slightly more matter than their surroundings. That additional matter increased the gravitational pull, attracting more matter still. The slightly less dense regions were drained of their matter, sending it toward the overdense neighbors. Over millions of years, then hundreds of millions, then billions, this process of gravitational amplification transformed the nearly imperceptible density variations of the early universe into the dramatic structures we see today. The universe sorted itself along the lines of its own initial conditions. What began as quantum noise became, over cosmic time, the walls and filaments and voids of the cosmic web. A typical cosmic filament stretches roughly 50 to 100 million light-years from end to end, and perhaps 10 to 20 million light-years across at its widest. It contains thousands of galaxies distributed along its length, separated from each other by millions of light-years of comparatively empty space, but concentrated relative to the surrounding voids in a way that makes the filament a genuine, overdense structure. Filaments are not static. Matter continues to flow along them, funneled by gravity toward the densest nodes where filaments intersect. These nodes, the galaxy clusters that sit at the convergence points of multiple filaments, are the most massive gravitationally bound structures in the universe. Between the filaments are the voids, vast, nearly empty regions that fill the majority of the universe's volume. The universe, by volume, is mostly void. The filaments and sheets and clusters that contain the overwhelming majority of the universe's matter occupy a surprisingly small fraction of the total space. If you were to place yourself randomly anywhere in the observable universe, the probability that you would find yourself inside a galaxy would be extraordinarily small. The probability that you would find yourself anywhere near a filament would be relatively small. The most likely outcome by an enormous margin is that you would find yourself inside a void, surrounded by nothing at all for hundreds of millions of light years in every direction. We are, from a probabilistic standpoint, remarkably lucky to live inside a galaxy. But luck is the wrong frame. We are here because the conditions that produce planets and stars and chemistry and eventually biology exist inside galaxies and not inside voids. The voids are not dangerous empty places. They are simply places where the prerequisites for our existence are absent. We are not located in the most probable place in the universe. We are located in one of the rarer places. The place is dense enough with matter and energy to permit the existence of anything complicated. The Bhuta's void is the best-known example of a cosmic void in our observable neighborhood. Discovered in 1981 when astronomers conducting a systematic survey of galaxy redshifts encountered an enormous region containing almost no galaxies, the Bhuta's void spans approximately 330 million light-years across. When the survey team first identified this structure, they were so surprised that they initially suspected a systematic error in their data. The absence of galaxies across such a vast region seemed to violate their intuitions about how matter should be distributed. Subsequent surveys confirmed the void was real. It was not an error in the data, it was the universe. Inside the Bhuta's void, the galaxy density drops to roughly 1% of the cosmic average. If you imagine our own galactic neighborhood with its hundreds of nearby galaxies within a few tens of millions of light years, and then imagine draining away 99% of those galaxies while keeping the volume the same, you begin to approach the density of the Bhuta's void. A civilization living on a planet inside the Bhuta's void would look out at a sky dramatically darker than ours. With no nearby galaxies, the faint smudges of light that human astronomers can see with the naked eye or small telescopes would simply not be there. The void sky would be almost entirely stars, stars from the hypothetical void galaxy, with nothing beyond them visible to any reasonably sized telescope until the instruments powerful enough to reach the void's edges came along. This is the landscape we are now traveling through, an alternating sequence of cosmic filaments teeming with galaxies and vast void regions where almost nothing exists, separated by transition zones where the galaxy density gradually rises or falls as matter thins or concentrates. The universe at this scale does not resemble a uniform distribution. It resembles something biological, something networked, something organized by principles of efficiency and flow that produce the same characteristic textures across enormous ranges of scale. Now, Woven through all of this structure, inseparable from it, is a phenomenon that we need to confront directly, because it is not just background scenery, it is the dominant physical process shaping everything at these scales and beyond. The universe is expanding, not in the intuitive sense of an explosion sending fragments outward through pre-existing space. In a more fundamental and stranger sense, space itself is expanding, and every point in the universe is moving away from every other point as a direct consequence of this expansion. There is no center of the expansion, there is no edge toward which the expansion is heading. The expansion is intrinsic to the metric of space, to the mathematical structure that defines distances between points, and it operates everywhere, simultaneously. The best analogy, imperfect as all analogies are, is a loaf of raisin bread rising in an oven. The raisins are the galaxies, the bread is the space between them. As the bread rises, every raisin moves away from every other raisin, not because any raisin is pushing or pulling the others, but because the medium that contains them all is expanding. A raisin near the center of the loaf and a raisin near the edge are both moving away from their neighbors at rates proportional to how far apart they are. The further apart two raisins are, the faster they appear to be separating, because there is more rising bread between them. This is exactly the behavior observed in the universe. Nearby galaxies bound by their mutual gravity do not separate. But galaxies separated by large enough distances where no gravitational bond is strong enough to resist the expansion recede from us at speeds proportional to their distance. Edwin Hubble established the observational foundation for this picture in 1929, demonstrating that distant galaxies moved away from us with velocities proportional to their distances. The relationship is now known as Hubble's law. The proportionality constant, the Hubble constant, describes how fast galaxies recede per unit of distance. Its current measured value sits at approximately 67 to 73 kilometers per second per megaparsec, a range that reflects an ongoing disagreement in modern cosmology that we will examine in detail shortly, because it touches something fundamental about what we know and do not know about the universe's history and future. At 1 billion light years, the expansion has had a billion years of unobstructed operation in the void regions, where no gravitational binding counteracts the outward push of the metric. In these regions, the expansion wins completely. Space opens beneath your hypothetical vessel at the full rate, with no galaxies or filaments nearby to slow or counteract the process. The void does not feel like anything because there is nothing in it to feel, but to an observer equipped with instruments sensitive to galaxy motions hovering at the center of a cosmic void, the surrounding universe would appear to be receding in every direction, the walls of the void pulling back like the inside surface of a slowly inflating bubble made of dark nothingness. Light crossing these voids carries the signature of the expansion in its wavelength. A photon emitted by a galaxy in a distant filament and traveling toward us across a void is stretched as it travels. The space it is moving through expands during the journey, and the photon's wavelength stretches with it, shifting from the shorter wavelengths of blue or violet light toward the longer wavelengths of red light. This cosmological redshift is not the same as the Doppler redshift of a moving ambulance siren. It is a consequence of the expansion of the metric itself, rather than any movement of the source through space. When we observe a galaxy with a large cosmological redshift, we are seeing light that has been stretched over the course of a long journey through expanding space, a journey whose duration we can calculate and whose starting point we can locate in cosmic time. The universe writes its own history in the color of its own light. In 1998, two independent teams of astronomers studying Type 1a supernovae in distant galaxies made a discovery that upended the theoretical expectations of virtually every cosmologist alive. Type 1. A supernovae are a specific kind of stellar explosion that occurs when a white dwarf star, the dense remnant of a dead sun-like star, accumulates enough mass from a companion star to trigger a runaway nuclear fusion reaction throughout its entire volume. Because this mechanism involves a very specific mass threshold known as the Chandrasekhar limit at approximately 1.4 solar masses, and because the physics of the explosion is driven by well-understood nuclear processes, these supernovae all release approximately the same amount of total energy. They are, in the language of astronomy, standard candles, objects of known intrinsic brightness that can be used to measure distances. If you can see a Type 1a supernova in a distant galaxy and measure how bright it appears from Earth, you can calculate exactly how far away it must be, because you know how bright it actually is. Both teams were using these standard candles to measure the expansion history of the universe. By looking at supernovae at different distances, and therefore at different epochs in the universe's past, they expected to chart how much the expansion had been slowing down over time. Gravity, acting on all the matter in the universe, should have been pulling against the expansion since the beginning, gradually decelerating it, perhaps eventually bringing it to a halt. The question they hoped to answer was how much deceleration had occurred, which would tell them the total matter density of the universe. What they found instead was that the expansion was not decelerating. The distant supernovae were dimmer than expected, which meant they were further away than expected, which meant the universe had been expanding faster than the standard models predicted. The universe was not slowing down, it was speeding up. The expansion of the universe is accelerating. Both teams checked their data. They searched for systematic errors. They considered alternative explanations. They found none that were satisfactory. The evidence was robust. The universe for the last 5 to 6 billion years had been expanding not at a decelerating rate, as every model had predicted, but at an accelerating rate, as if something were pushing space apart with increasing force rather than gravity's pull gradually applying the brakes. Both teams shared the Nobel Prize in Physics in 2011 for this discovery, which remains one of the most consequential observational results in the history of cosmology. The something responsible for this acceleration has been named dark energy. It is described as a property of empty space itself, an energy density that does not dilute as the universe expands, that remains constant per unit volume, even as the universe grows larger, and that therefore becomes more and more dominant over time, as the matter density falls with the expanding volume while the dark energy density remains constant. Currently, dark energy accounts for approximately 68% of the total energy content of the observable universe. Ordinary matter, everything made of protons and neutrons and electrons, everything we can see and touch and measure, accounts for roughly 5%. Dark matter, the invisible gravitational scaffolding inferred from its effects on galaxies and clusters but never directly detected, accounts for approximately 27%. The universe is, by energy content, 95% invisible, and 68% of it is actively accelerating the expansion. We do not know what dark energy is. The name itself is an admission of ignorance, dressed up as a label. The simplest theoretical description treats it as a cosmological constant, a fixed energy density of the vacuum, and this description fits every observation we have so far. But the cosmological constant raises a deep theoretical problem. Quantum field theory, our best framework for understanding the fundamental constituents of matter and energy, predicts that empty space should contain a vacuum energy arising from quantum fluctuations of all the fields that permeate the universe. The predicted value of this vacuum energy is roughly 120 orders of magnitude larger than the observed value of the cosmological constant. 120 orders of magnitude, a factor of 10 followed by 120 zeros. This is the largest discrepancy between theoretical prediction and observational measurement in the entire history of physics. And it has been called, without exaggeration, the worst prediction ever made by a successful physical theory. This mismatch tells us something important. We are missing something fundamental about the relationship between quantum mechanics and gravity. The two greatest theoretical frameworks in physics are, at this level, deeply inconsistent with each other. Quantum field theory predicts a vacuum energy that would produce a cosmological constant so large it would have caused the universe to accelerate so violently in its earliest moments that no stars, planets, or anything else could ever have formed. The universe, we observe, has a cosmological constant small enough to have permitted 13.8 billion years of structure formation. Why the observed value is what it is, rather than the predicted value, is one of the central unsolved problems in theoretical physics. Several Nobel laureates have described it as the deepest puzzle in science. What dark energy does to the universe over long time scales is as important as what it is. Because it causes accelerating expansion, the regions of the universe not gravitationally bound to each other are being pulled apart at ever-increasing rates. Galaxies within the local group are gravitationally bound and will not be separated by the expansion. But galaxies in distant clusters, separated from us by hundreds of millions or billions of light years, are receding faster than they used to recede, and will recede faster still in the future. As the acceleration continues, more and more distant galaxies will eventually reach recession speeds that redshift their light beyond any detectability, and they will pass over what cosmologists call the cosmic event horizon, the boundary beyond which no future light they emit can ever reach us, because the space between us is expanding faster than light can traverse it. In 100 billion years, give or take, essentially every galaxy outside our local group will have crossed this horizon. The observable universe will consist of the merged remnant of the Milky Way and Andromeda, surrounded by the other members of our local group, and nothing else. Any civilization existing in that future universe, looking out at the sky with the most powerful telescopes imaginable, will see no distant galaxies, no cosmic web, no evidence of the vast structure that we can observe today. They will look out at emptiness and conclude, if they conclude anything at all, that the universe consists only of their local island of stars. They will have no way of knowing that billions of other islands once existed and have since retreated beyond the reach of light. The universe will have become cosmologically lonely in a way that ours currently is not. We live in a privileged moment. The cosmic web is visible to us now. It will not always be. At 350 million light-years, our journey takes us through the region containing the Coma cluster, one of the most extensively studied galaxy clusters in astronomy. The Coma cluster contains over 1,000 galaxies within a region roughly 20 million light-years across. Its total mass, including the dark matter halo that envelops and outweighs the visible galaxies by a large factor, is estimated at approximately 10 to the power of 15 solar masses, a quadrillion times the mass of our Sun. Most of that mass is not in any galaxy. It is in the hot intracluster gas that fills the space between the Coma cluster's galaxies, a diffuse plasma heated to tens of millions of degrees by the cluster's gravitational compression, radiating energy across the X-ray portion of the spectrum. And beyond even the gas, invisible and inferred only from its gravitational effects, is the dark matter that makes up the majority of the cluster's total mass. The Coma cluster has historical significance beyond its physical properties. In 1933, the Swiss astronomer Fritz Zwicky studied the velocities of galaxies within the Coma cluster and noticed something wrong. The galaxies were moving far too fast to be held in the cluster by the gravitational pull of the visible matter alone. If the only gravity came from the stars and gas that could be seen, the cluster should have flown apart long ago. The galaxies were moving as if there were far more mass in the cluster than could be accounted for by anything visible. Zwicky coined the term dunkle Materie, dark matter, to describe this invisible but gravitationally significant substance. His observation was largely ignored or dismissed for decades. It was only in the 1970s and 80s, as evidence accumulated from galaxy rotation curves, gravitational lensing, and large-scale structure analysis, that dark matter became an accepted cornerstone of the standard cosmological model. This is one of the striking patterns in the history of science at these scales. The universe consistently contains more than it shows. The visible matter is a minority. The matter that produces radiation of some kind is a minority. Even dark matter, the invisible gravitational scaffolding that makes up most of the matter in the universe, is itself a minority of the total energy content, outweighed by the dark energy that drives the expansion. Layer after layer of the cosmos turns out to conceal more layers beneath. The universe is not opaque in a simple sense. It is stratified into a hierarchy of scales of hiddenness, each one revealed only by the development of the theoretical and observational tools capable of detecting its specific signature. Pushing through 450 million light-years, we cross the region containing the Sloan Great Wall. Identified in 2003 from data collected by the Sloan Digital Sky Survey, this massive structure stretches approximately 1.37 billion light-years across in its longest dimension, making it, when discovered, the largest known structure in the observable universe. It is a filamentary superstructure, a concentration of galaxy clusters and groups strung along a shape that resembles a crumpled sheet more than a simple linear filament, containing thousands of galaxies distributed across a volume that challenges the predictions of our best cosmological models. The challenge is specific and worth examining carefully. In the standard cosmological framework, the universe should become homogeneous and isotropic at scales above roughly 300 to 400 million light-years. The cosmological principle, the foundational assumption of modern cosmology, predicts that no structure larger than this should exist, because the gravitational processes that build structures require causal contact between their parts, and at scales above a few hundred million light-years, the different parts of a potential structure have never been in causal contact in the history of the universe. They have never exchanged signals. Gravity has never had time to coordinate their assembly into a unified structure. The Sloan Great Wall is more than 1 billion light-years long. It is 3 to 4 times larger than the theoretical upper limit. Some cosmologists have argued it is a projection artifact, a chance alignment of separate structures that appear connected in two-dimensional survey maps, but are actually unrelated in three-dimensional space. Others have argued the data supports a genuinely coherent structure. The debate remains active, but its existence, confirmed or not, is one of several observations that press uncomfortably against the cosmological principle, asking whether the universe's large-scale structure is genuinely as uniform as our foundational assumptions require. The most extreme challenge to these assumptions arrived in 2013 with the announcement of the Huge Large Quasar Group. Quasars are among the most luminous objects in the observable universe, the brilliantly radiating cores of galaxies in which supermassive black holes are actively consuming enormous quantities of surrounding gas and dust, converting that in falling matter into energy with an efficiency that makes nuclear fusion look modest. The most luminous quasars outshine their host galaxies by factors of thousands, making them visible across distances that galaxy surveys cannot easily reach. Because quasars can be seen from much greater distances than ordinary galaxies, they can be used to probe the large-scale structure of the universe at scales where galaxy surveys run out of sensitivity. The Huge Large Quasar Group contains approximately 73 quasars distributed across a region estimated at roughly 4 billion light-years in its longest dimension, 4 billion light-years, in a universe that is only 13.8 billion years old, a structure whose light-crossing time spans more than a quarter of the entire age of the universe. If this structure is a genuine, physically coherent entity, rather than a statistical clustering artifact, it is not merely a record breaker. It is a crisis for the cosmological principle. A structure 4 billion light-years across cannot have formed through any known gravitational process in a universe with a finite age and a finite causal horizon. The physics simply does not permit it. The response from the cosmological community has been mixed. Some researchers have argued that the statistical methods used to define the Huge Large Quasar Group as a coherent structure are not adequate to distinguish a real physical association from a random clustering fluctuation. Others have found the structure compelling and have argued it requires modification of the standard model. The argument continues. What is not in question is that objects at this scale exist and that mapping their distribution pushes our theoretical frameworks to their limits. There is a principle so central to modern cosmology that without it, the entire mathematical framework of the field collapses. It is called the cosmological principle, and it states, in the most precise terms available, that the universe is homogeneous and isotropic at sufficiently large scales. Homogeneous. The universe has the same average properties at every location. No region is fundamentally different in composition or density from any other region when averaged over large enough volumes. Isotropic. The universe looks the same in every direction. There are no preferred axes, no special orientations, no directions along which the universe is systematically different from other directions. These two properties together imply that no point in the universe is privileged, that the laws of physics and the large-scale structure that they produce are the same everywhere and in all directions, and that any observer anywhere in the observable universe would see, at the largest scales, the same universe we see, This principle is not arbitrary or ideological. It is deeply and repeatedly tested by observation. The cosmic microwave background radiation, the thermal glow left over from when the universe was approximately 380,000 years old and cool enough for electrons and protons to combine into hydrogen atoms for the first time, is our best window into the early universe. It is extraordinarily uniform. The temperature of the cosmic microwave background varies by only about 30 microkelvins across the entire sky, a variation of roughly 1 part in 100,000 against an average temperature of 2.73 Kelvin. This near-perfect uniformity is direct evidence that the early universe was extraordinarily homogeneous. The density fluctuations that would eventually grow into the cosmic web were present but tiny, whispers of variation in a universe that was, to an extraordinary degree, the same everywhere. The cosmological principle has also been confirmed by galaxy surveys that show the large-scale distribution of galaxies becoming increasingly uniform as the averaging scale increases. At scales of a few hundred megaparsecs and above, the statistical properties of the galaxy distribution converge to a smooth, isotropic average. The cosmic web structures we have been traveling through, dramatic and striking as they are at scales of hundreds of millions of light-years, are, at the level of the cosmological principle, small perturbations on a fundamentally smooth background. But the structures we have encountered in this journey, the Sloan Great Wall at over 1 billion light-years, the huge large quasar group at 4 billion, and, most disturbingly, the Hercules Corona Borealis Great Wall, announced in 2013 and 2014 and estimated to span approximately 10 billion light-years in its longest dimension, all cite at scales where the cosmological principle says coherent structures should not exist. They are not small perturbations. They are, if real, systematic violations of homogeneity at scales that the standard model says should already be smooth. The Hercules Corona Borealis Great Wall was identified using the distribution of gamma-ray bursts, rather than galaxy positions. Gamma-ray bursts are the most energetic electromagnetic events in the observable universe. Brief but incomprehensibly powerful flashes of gamma radiation that appear to arise primarily from the collapse of massive stars into black holes or from the mergers of neutron stars. Because of their extreme brightness, they can be detected across distances that no other individual astrophysical event can match. If gamma-ray bursts trace the underlying distribution of matter in the universe, their spatial distribution can be used to map the largest scale structures. The team that identified the Hercules Corona Borealis Great Wall found a statistically significant excess of gamma-ray bursts in a region of sky covering a volume estimated at 10 billion light-years in its greatest extent. 10 billion light-years. The observable universe itself is approximately 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall, if it is a genuine physical structure, spans roughly 1/9 of that diameter. A causal signal travelling at the speed of light would take 10 billion years to cross it, which is longer than the universe had existed when the structure supposedly began to form. The physics of structure formation through gravitational processes is unambiguous. Structures of this scale cannot be causally connected in a 13.8 billion-year-old universe. There are three coherent responses to this tension. The first is to question the methods. The statistical identification of large-scale structures from point source distributions like gamma-ray bursts involves assumptions about clustering algorithms and significance thresholds that are genuinely debatable. If the clustering analysis overestimates the coherence of the distribution, the structure may be much smaller or may not exist as a unified entity at all. This is a legitimate scientific concern, and ongoing work continues to refine the analysis. The second response is to extend the scale of homogeneity. Perhaps the cosmological principle is valid, but requires averaging over volumes much larger than previously thought before homogeneity kicks in, which would make the principle very difficult to test, given the finite size of our observable universe, and would require explaining why the transition to homogeneity occurs at a much larger scale than theoretical models predict. The third response is to take the structures seriously as evidence that the standard model of cosmology is missing something important, that the physics governing structure formation at the largest scales is not fully captured by our current framework. None of these responses is comfortable. All of them require giving something up, either precision in our statistical methods or testability of our foundational principles, or confidence in our most successful cosmological framework. Science is never comfortable at its frontiers. It is, however, honest about its discomfort, and the ongoing debate about large-scale structure is one of the most honest conversations in contemporary cosmology. There is another frontier of discomfort that has been building throughout this journey and now demands its full examination. It is called the Hubble tension, and it is the kind of problem that, if it persists and if the current interpretations are correct, will require a revision to our understanding of the universe's history at a fundamental level. The Hubble constant, the number that describes how fast the universe is expanding per unit of distance, can be measured in two fundamentally different ways. The first way uses the cosmic microwave background, the early universe's thermal relic, as the starting point. By analyzing the detailed pattern of temperature fluctuations in the cosmic microwave background, cosmologists can extract the universe's density parameters with extraordinary precision, plug those parameters into the standard cosmological model, and calculate what the expansion rate should be today. This method gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second way uses the cosmic distance ladder, a chain of distance measurements calibrated against each other, beginning with parallax measurements of nearby stars, extending to pulsating, Cepheid variable stars in nearby galaxies whose luminosity is tightly correlated with their pulsation period, and ultimately reaching to the Type 1a supernovae we encountered earlier as standard candles for distances of hundreds of millions and billions of light-years. This method, which is entirely independent of any cosmological model, gives a Hubble constant of approximately 73 kilometers per second per megaparsec. These two values are inconsistent with each other. The discrepancy between 67.4 and 73 is approximately 9%, and the statistical significance of this discrepancy has grown steadily as measurement precision has improved. As of the most recent analyses, the tension stands at roughly 5 standard deviations, a level at which physicists typically declare a genuine discovery rather than a statistical fluctuation. The probability that the discrepancy is a random statistical error is less than 1 in 3 million. Both measurements are robust. Both have been checked by multiple independent teams using different instruments and different calibration methods. The error bars have been pushed down as far as current technology allows, and the discrepancy remains. Something is wrong with our picture of the universe's expansion history. The implications are profound. If the early universe measurement and the late universe measurement are both correct, then the expansion rate of the universe changed between the early and late epochs in a way that the standard cosmological model, lambda cold dark matter, does not predict. Something happened to the expansion. Something intervened between the early universe and the present to accelerate it beyond what the standard model accounts for. Proposed explanations include an early dark energy component that was stronger in the first few 100,000 years of the universe's history before fading away, a decay of a previously unknown particle species that transferred energy to the expansion, a modification of the behavior of dark matter in the early universe that shifted the acoustic scale measured in the cosmic microwave background, and several modifications to general relativity itself that would change the expansion dynamics at specific epochs. None of these proposals fits all the data cleanly. None has been confirmed. The Hubble tension is not a solved problem dressed up as a mystery. It is a genuine unresolved discrepancy at the heart of cosmology, and its resolution, whatever form that resolution takes, will almost certainly reveal something new about the physics of the universe that we currently do not know. What the Hubble tension means for our journey is this. Every distance we have quoted, every filament we have located, every structure we have placed at a specific number of light years from Earth carries an uncertainty that is tied to the Hubble constant we assumed in the calculation. If the true Hubble constant is different from what we currently believe, all of our cosmological distances need to be rescaled accordingly. The map of the universe is exquisitely detailed and extraordinarily well tested, but it may have a systematic error in its scale bar, and that error traces directly to our incomplete understanding of what the universe is made of and how its expansion has evolved. We are now at 800 million light-years from Earth. The cosmic web continues around us in every direction. Filaments thread the space between voids that span hundreds of millions of light-years. The expansion presses outward everywhere with dark energy's patient force. The light, reaching us from any direction, has been traveling for hundreds of millions to billions of years before arriving at the instruments we have built to receive it. We are inside a sphere of receivable information, a bubble of the knowable, surrounded in every direction by a universe that exists beyond our observational horizon and will remain forever inaccessible to any observation we can make. Let us now perform the thought experiment at the heart of this journey. Let us stand at 980 million light-years from Earth and look back. The Milky Way is not visible as an individual object to the unaided eye, even a hypothetical eye hovering in space. At this distance, our galaxy subtends an angle in the sky so small that the difference between the Milky Way and any of the thousands of other faint smears of galaxies in the same visual field is indistinguishable without specialized instruments. Every direction you look contains the same faint scatter of galaxy light, the same tendrils and nodes of the cosmic web, the same receding tide of a universe that does not know or care that you are trying to find home in it. The light, arriving at your position from the direction of the Milky Way, left our galaxy approximately 1 billion years ago. Earth, at that moment, was a world in the Neoproterozoic era. The atmosphere was breathable by today's standards in terms of oxygen content, though the exact composition remains debated. The land masses were organized into configurations utterly unlike those of the present. The supercontinent Rodinia was in the process of breaking apart, its fragments beginning the long drift that would eventually produce the familiar arrangement of continents. The oceans were populated by microbial life and perhaps the earliest simple multicellular organisms, soft-bodied creatures leaving almost nothing in the fossil record so early in the elaboration of complex life that calling them animals is a generous extension of the term. There were no trees, no insects, no fish, no bones, no shells, nothing that could look at the sky and wonder. The human species was more than 950 million years in the future. Every civilization, every language, every written word, every thought recorded in any medium, every act of love or war or curiosity or creation that humans have ever performed was separated from that moment by a gap of time comparable to the entire history of complex animal life on Earth. The light arriving at your position carries images of a planet that has no memory of us, a planet that has not yet become a world that could produce the minds trying now to understand it. And the Earth of the present moment, the Earth on which these words exist, is invisible to you from this position. The light from today's Earth is in transit. It left a moment ago. It is crossing the universe toward your hypothetical vantage point at the speed of light, and it will not arrive for approximately 1 billion years. You are separated from the present by exactly the same distance that separates you from the past. There is no way from this location using any physical instrument to observe the Earth as it currently exists. The laws of physics enforce this separation absolutely. The finite speed of light is not a limitation that better technology will overcome. It is a structural feature of a universe that contains neither absolute simultaneity nor any faster-than-light signaling mechanism. Every observer in the universe is surrounded by a spherical horizon of receivable information, the cosmic equivalent of the visible horizon on a curved Earth surface. Beyond your horizon, events are happening right now. Stars are forming and dying. Galaxies are interacting. Perhaps minds exist, organized from the same physical principles that organized ours, looking out at their own horizons and finding them equally bounded. We will never know. The universe's causal structure guarantees that the vast majority of what is happening in it, even in this moment, is permanently invisible to us, not invisible because of atmospheric conditions or telescope sensitivity or funding constraints. Invisible because the light from those events has not had time to reach us, and in an accelerating universe, some of it never will. The concept of the universe as it currently exists, simultaneously, everywhere, at once, the concept of a cosmic now, is not merely unmeasurable. In the framework of relativity, where simultaneity is observer-dependent and no universal time coordinate exists, the cosmic now is not even a well-defined concept. Different observers moving relative to each other disagree about which events in distant locations are happening simultaneously with any given local event. No observer's simultaneity is more correct than any other's. The universe does not have a single present. It has a vast web of causal relationships, light cones connecting past events to future consequences, and everything outside any given observer's past. Light cone is, in a precise sense, outside their universe. Push the final 20 million light years. We are at 1 billion light years from Earth. Turn to face the other direction, away from home, outward into the rest of the observable universe, which from this location still extends approximately 45 billion light-years in every outward direction, before reaching the cosmological horizon defined by the age of the universe and the speed of light. What you see is the continuation of everything you have travelled through. More filaments, more voids, more clusters strung along invisible gravitational scaffolding. More of the cosmic web extending in every direction to the limit of the observable. The universe from here does not look like it is ending. It does not look like it is approaching any edge. The cosmological principle holds. The large-scale properties of the universe are the same here as they are from Earth. The same expansion rate, the same dark energy density, the same average matter density, the same physical laws operating at every scale from the quantum to the cosmological. The universe at 1 billion light-years from Earth is the same universe as Earth's universe. There is no break, no discontinuity, no boundary where the familiar ends and the alien begins. Only the same web, the same vacuum, the same accelerating expansion, extending in every direction to the limit of what light has had time to show us. And yet something has changed. Something about the perspective changes when you have travelled far enough to see the web. From inside the local group, the universe looks lumpy and structured and complex and specific. Individual galaxies are distinct objects with distinct histories. The night sky is populated by named stars with named planets. The universe feels, from close enough, like a collection of things. But at 1 billion light-years, you can see that those things are not the fundamental reality. They are local expressions of a single underlying process. The web is the reality. The galaxies are concentrations within it. The stars are concentrations within the galaxies. The planets are concentrations within the stellar systems. The organisms on those planets are concentrations within the planetary chemistry. All of it is matter organized by the same forces, at the same scales, following the same rules, from the first quantum fluctuation in the first instant after the Big Bang to the mind reading these words in whatever moment they happen to be read. This is what 1 billion light-years reveals that nothing closer can reveal. The universe is not a collection of objects. It is a single ongoing process, a continuous unfolding of complexity from uniformity, of structure from chaos, of pattern from noise, governed by physical laws whose mathematical form appears to be the same in every corner of the observable universe. The cosmic web is not just the largest structure we can map. It is the signature of that process, written in matter at the scale where it first becomes legible. To stand here and look at it is to see the universe in a way that no human has ever literally seen it, and yet to understand what you are seeing in a way that becomes possible only through the accumulated effort of thousands of scientists over centuries, building instruments and theories and mathematical frameworks of extraordinary precision and testing them against the universe's own record of its history. The image in a modern cosmological survey showing the filaments and voids of the cosmic web is not a photograph in any simple sense. It is a reconstruction, a synthesis of spectroscopic measurements, photometric calibrations, distance ladder calculations, statistical analyses, and theoretical frameworks, all combined into a picture of the universe that would have been impossible for any single mind to produce alone, and that becomes more accurate with every new instrument brought online. There is something that needs to be said about the people who built those instruments and developed those frameworks, not the famous names in the history of physics, but the entire human enterprise that produced them. Every telescope is a triumph of engineering. Every spectrograph that separates light into its component colors is a triumph of optics and manufacturing. Every survey that maps millions of galaxies is a triumph of computing and data analysis and institutional coordination. Every theoretical framework that makes quantitative predictions about the universe's structure is a triumph of mathematical imagination. None of this was inevitable. None of it was easy. All of it was the product of specific human beings in specific historical circumstances making specific choices to dedicate their working lives to understanding something that had no immediate practical application and offered no obvious material reward beyond the understanding itself. The entire apparatus of modern cosmology, from the 2.5-meter Hooker telescope at Mount Wilson that Hubble used in the 1920s, to the James Webb Space Telescope operating today at a gravitationally stable point, 4 times the distance from Earth to the Moon, represents the accumulated investment of an entire civilization in the project of understanding its own context. We built these instruments not because we needed to for survival. We built them because we are the kind of thing that builds them. The kind of thing that looks at a faint smear in the sky and wants to know what it is and how far away it is and what it is made of and how it got there. That drive is not separate from the rest of what we are. It is the same drive that produces art and philosophy and mathematics and music. The same capacity for pattern recognition that finds structure in the cosmic web finds beauty in a Bach fugue. The same ability to hold complex systems in working memory that allows a cosmologist to manipulate the mathematics of general relativity allows a novelist to maintain the internal consistency of a fictional world. The same compulsion toward understanding that sends telescopes into orbit sends philosophers into libraries and archaeologists into excavations and poets into the difficult work of finding precise language for imprecise experience. We are, as a species, creatures that make maps of things larger than ourselves, and cosmology is the largest map we have attempted. Standing at 1 billion light-years from Earth, at the edge of what our maps currently reach with full confidence, looking out at a universe that extends for tens of billions of light-years beyond in every direction, the most honest thing to say is, we have barely started. The observable universe is a sphere 93 billion light-years across. We have mapped, with decent resolution, perhaps a few % of that volume. The rest is inference, extrapolation, statistical theory. The physics we are confident about holds at every scale we have tested, and we have reason to expect it extends beyond those scales. But the expectation is not the same as the evidence. Beyond the observable universe, there may be more universe, possibly an infinite amount. The inflationary models that describe the Big Bang's first moments, the same models that explain the near-perfect uniformity of the cosmic microwave background, predict that the universe extends enormously beyond what we can observe. Some versions of inflation predict an infinite universe of which our observable portion is a vanishingly small sample, a bubble of causal contact, floating in an infinite sea of space that we will never observe and never reach. Other versions predict a much larger but finite universe. We cannot currently distinguish between these possibilities because the evidence required to do so lies permanently beyond our observational horizon. The universe may contain multitudes we will never know. And this is where the journey arrives at its deepest point, the point that cannot be reached by instruments or equations, but only by sitting with the full weight of what the observations reveal. We are conscious. In a universe of 400 billion galaxies, each containing hundreds of billions of stars surrounding a cosmos that may be infinite in extent, consciousness is, as far as we can determine from any observation or theory, confined to a thin biological film on a single small planet orbiting an ordinary star in the outer regions of an unremarkable spiral galaxy. Possibly consciousness exists elsewhere. Probably, given the numbers, it does, but we have found no evidence of it beyond our own world, and in the absence of that evidence, we must hold our own existence as the only confirmed example of the universe knowing itself. The universe does not know itself through any mechanism we can identify other than the minds that exist within it. The dark energy does not experience its own expansion. The filaments of the cosmic web do not feel their own gravity. The voids do not register their own emptiness. The billions of years of structure formation, the quantum fluctuations amplified by gravity into galaxies and clusters, the entire elaborate history of cosmic evolution from the first second to the present unfolded in the dark, without witness until the late and local and temporary appearance of organisms capable of reconstructing that history from the clues left in light and matter and the mathematics of physical law. We are those organisms, not special in the cosmic sense. We are made of the same atoms as everything else, governed by the same forces, as temporary as any other configuration of matter, but unique in the sense that matters. We are aware. We are aware of the web. We are aware of the expansion. We are aware of the dark energy pulling the universe apart and the long, cold future it promises. We are aware of our own insignificance and find it, rather than crushing, somehow clarifying. There is a question that has haunted physics since Einstein. Why is the universe comprehensible? Why should a universe that did not require any observer to exist, that would have unfolded exactly as it did whether or not any mind ever arose to observe it, be governed by laws elegant enough to be written down on a few sheets of paper and powerful enough to correctly predict phenomena across 60 orders of magnitude of scale? This is not a rhetorical question. It is a genuine philosophical puzzle. A universe could exist with physical laws so complicated, so context-dependent, so variable from place to place and moment to moment, that no local observer could ever infer global regularities from local measurements. Such a universe would be, from the perspective of any observer within it, fundamentally incomprehensible. Our universe is not like that. It is, at every scale we have tested, orderly, mathematical, and consistent. The same equations that describe the motion of a pendulum describe the orbit of a planet. The same quantum mechanics that governs the electron in a hydrogen atom governs the nuclear reactions in the core of a star, a billion light years away. Why this should be the case, nobody knows. Whether it will remain comprehensible as we press into the regimes of quantum gravity and cosmological scales beyond the observational horizon is an open question. But the comprehensibility we have encountered so far is itself one of the most remarkable facts revealed by looking at the universe from 1 billion light years away, because at this distance you can see that the comprehensibility is not local. It is cosmic. The same laws that you can write down in a notebook on a small planet apply, without modification, to the largest structures we have ever mapped. The light from the present-day Earth is traveling toward this location right now. Photons leaving the Sun's surface today, scattering off the Earth's atmosphere and oceans and land masses, are beginning the billion-year journey that will end at the position we now occupy. In 1 billion years, those photons will arrive. They carry the signature of a world with liquid water and an oxygen atmosphere, with continents and polar ice caps, with the particular spectroscopic fingerprints of a biosphere in full activity. Whether there will be any instrument at this location in 1 billion years to receive them and read their message is a question that the universe declines to answer. Whether any descendant of any living thing on Earth today will exist to have built such an instrument is equally unanswerable. The photons do not know or care. They travel because that is what photons do. They carry their information because that is what light does. The universe records and transmits without regard for whether the transmission is received. But we are receiving. Today, at this moment, we are receiving the light from 1 billion years ago and building from it a picture of a universe whose structure we can map and whose history we can reconstruct and whose physical laws we can write down. That act of reception and reconstruction is not guaranteed by the laws of physics. It requires not just the existence of instruments, but the existence of minds willing to point instruments at the sky, willing to spend years analyzing the data, willing to argue about the implications, willing to be wrong and correct themselves and try again. It requires an entire civilization that values the project of understanding its own context enough to sustain the institutions and investments that make such understanding possible. We are, in the universe's long history, an extremely recent development. The universe is 13.8 billion years old. Complex animal life on Earth is approximately 540 million years old. Modern humans have existed for perhaps 300,000 years. Scientific astronomy, in the sense of quantitative measurement and mathematical modeling, has been practiced for perhaps 500 years. The most powerful cosmological instruments humanity has ever built have been in operation for less than 30 years. In the 13.8 billion year history of the universe, we are a story that has barely begun. And yet, in those few hundred years of looking, we have traced the universe's history from the first second after the Big Bang to the present. We have measured the cosmic microwave background and confirmed the universe's early uniformity to 1 part in 100,000. We have mapped the cosmic web across hundreds of millions of light years. We have identified the existence of dark matter and dark energy and determined their relative abundances. We have discovered the accelerating expansion. We have imaged a black hole. We have detected gravitational waves from colliding black holes and neutron stars. We have found thousands of planets orbiting other stars. We have traced the nuclear reactions that build the elements in stellar interiors and scatter them through supernova explosions into the interstellar medium, from which new stars and planets and, eventually, organisms are built. We have, in summary, understood the physical story of the universe from its first moments to its current structure and its likely future. Not completely, not without uncertainty and ongoing debate, but in broad and increasingly precise strokes. We have read the universe's autobiography from the fossil light it has left across cosmic space. We have done this in the blink of a cosmic eye, from a single small planet, using instruments we built from first principles and mathematics we developed from scratch. That is not a small thing. That is, arguably, the most remarkable thing we know of. The journey home is, in the physics, the same as the journey out. Space has no preferred direction. The laws are the same in every direction. The expansion continues regardless of which way you face. But in the experience of this thought experiment, in the felt sense of having covered 1 billion light years of universe and turned back, the return is not the same. Laniakea is not just a gravitational watershed now, it is the address of everything you have ever known. The Milky Way, when it resolves from a faint smear into a recognizable spiral, is not just a galaxy. It is the galaxy where something happened that has not, as far as we know, happened anywhere else. The universe developed the capacity to understand itself. Whether that capacity is unique or common, whether the universe is full of minds looking out at the same web from different positions in it, whether the comprehension of the cosmos by conscious minds is a rare anomaly or a natural consequence of a universe old enough and large enough for complexity to arise in many places, we cannot yet say. We do not know. The data does not yet tell us. The search is ongoing, and the answer, if it comes, will be the most significant scientific result in human history. But here is what the data does tell us, what it tells us with confidence and precision from this vantage point of 1 billion light years. The universe is vast beyond imagining and structured beyond expecting and old beyond feeling, and accelerating toward a future in which everything currently visible will eventually recede beyond all possible observation. The web will dissolve. The clusters will survive for a while, then the stars within them will go out one by one over time scales of trillions of years. Eventually, even the protons that make up ordinary matter may decay if certain theoretical predictions are correct, leaving a universe of black holes slowly evaporating in an accelerating void, finally giving way to a darkness of maximum entropy from which nothing new can arise. That is the long ending. It is very long. The timescales involved make the current age of the universe look like the first breath of an existence that will continue for a duration that makes 1 billion light years seem close and quick. But it is the ending that the physics points toward, and at 1 billion light years from Earth, with dark energy already pulling the future into shape, you can feel the direction of travel. And yet, the universe produced you. Not you specifically, but the kind of thing you are, a pattern of matter organized into awareness, capable of asking where it came from, and where it is going, and what it is embedded in. The universe did not need to be comprehensible to produce you. It did not need to follow mathematical laws that can be written down by a mind made of atoms. It did not need to leave fossil light in the cosmic microwave background that encodes its early history with such clarity that we can read it tens of billions of years later. It did not need to organize itself into a web whose structure reflects the quantum fluctuations of its first moments with such fidelity that we can trace our present architecture back to the universe's infancy. But it is all of those things. And you, standing here at 1 billion light years from home, aware of the web and the expansion and the dark energy and the long, cold future, are the evidence that those properties of the universe are not wasted. They are not properties of a universe that exists only for itself, indifferent to its own structure. They are properties of a universe that, at one small location among billions, became self-aware. The universe, through you, knows that it is vast. The universe, through you, knows that it is old. The universe, through you, knows that it is structured and lawful and temporary and, in the deepest sense of a word, that the universe itself cannot feel, but that you can. Beautiful. That is not nothing. At 1 billion light years from Earth, with the cosmic web stretching in every direction and the expansion continuing in every direction, and the darkness of the voids extending in every direction, that is, in fact, everything. The light from home is still in transit. It will take 1 billion years to arrive, but it is coming. The universe does not forget. It only expands, and in the patient widening of the space between all things, in the slow and certain dissolution of everything the cosmos has built across its entire history, there remains, for now, a small and temporary brightness, one pale blue point of light in one unremarkable corner of the web, where matter looked at itself and asked, "What is all of this?" and meant it. There is one more thing that needs to be said before this journey is truly complete, one thread that has been present in every section of this exploration without ever being named directly. It is the thread of time itself, not cosmic time in the sense of billions of years, but the specific and personal time of the person reading or hearing these words. You have spent real hours with this material. You have followed the scale from the Moon to the heliopause, to Proxima Centauri, to the Milky Way, to Andromeda, to the local group, to Laniakea, to the cosmic web, to the theoretical edges of what we know. You have absorbed the discovery of dark energy and the mystery of the Hubble tension and the challenge posed by structures larger than our models say should exist. You have stood, in imagination, 1 billion light years from everything you have ever known and looked back at a point of light that does not know you are looking. That investment of time is not trivial, and it raises a question worth examining directly. Why does any of this matter to a person living an ordinary life on the surface of an ordinary planet? The answer that scientists typically give is that knowledge has intrinsic value, that understanding is its own reward, that curiosity is a fundamental human drive that deserves to be satisfied. All of that is true, but it is not the deepest answer. The deepest answer has something to do with scale, and with what happens to a person when they genuinely internalize the scale of the universe rather than merely acknowledging it intellectually. Most of the anxieties that consume human attention are, at cosmic scale, vanishingly small. The disagreements that generate the most heat in daily life, the frustrations and disappointments and social conflicts and professional setbacks are real experiences with real emotional weight. They deserve to be taken seriously as human experiences, but they exist within a context that most people never fully confront. The context of a universe 14 billion years old and 1 billion light years deep and filled with 400 billion galaxies, each containing hundreds of billions of stars, most of which will continue to burn long after the last trace of anything human has dissolved back into the atomic substrate from which it briefly arose. That context does not diminish the difficulties of a human life. It reframes them. It places them inside a larger story, a story in which the fact that conscious matter exists at all and asks questions about its own origins is more astonishing than any individual human success or failure. It is a perspective that ancient philosophers sought through meditation and ascetic practice, the perspective of the overview. Astronauts who see Earth from orbit describe a cognitive shift that many of them report as the most significant experience of their lives. The sudden visceral understanding that the borders and conflicts and urgencies that define political life on Earth are features of a small surface on a small rock in an incomprehensible sea. That understanding does not erase the importance of human affairs. It clarifies them. It separates what genuinely matters from what merely feels urgent. The journey we have taken is a version of that overview, translated into the medium of language and physics rather than the medium of a rocket and a window. Its purpose is not to make human life feel small and therefore meaningless. Its purpose is the opposite, to make human consciousness feel large and therefore extraordinary. Because consciousness, as we have established, is the only known mechanism by which the universe achieves self-knowledge. And self-knowledge at any scale is among the most valuable things that can exist. Consider what it means that the atoms in your body have a history. Every hydrogen atom in every water molecule in every cell of your body was formed in the first 3 minutes after the Big Bang, when the universe cooled enough for protons and electrons to briefly bond into hydrogen before the radiation density tore them apart again. Those hydrogen atoms are 13.8 billion years old. The heavier atoms, the carbon and oxygen and nitrogen and iron that give your body its structure and its chemistry, were synthesized in the cores of stars that lived and died before the sun existed. The calcium in your bones was forged in stellar nuclear reactions and scattered through space in supernova explosions billions of years before the solar system formed. You are, in the most literal and precise sense, made of stardust, not as a poetic metaphor, as a statement of nuclear astrophysics. Those atoms spent billions of years drifting through interstellar space, cycling through generations of stars, being incorporated into gas clouds and planetary surfaces, and simple chemistry before the particular arrangement of circumstances on one small planet in one outer spiral arm produced the conditions for life, and then for complex life, and then for conscious life, and then for the specific concatenation of biological and cultural evolution that produced a mind capable of tracing the journey those atoms had taken. The atoms in your brain right now are the universe reflecting on its own history. They are the cosmic web thinking about itself. This is not mysticism. It is physics. And it is physics that carries philosophical weight that no amount of academic distancing can fully neutralize. You are not separate from the universe. You are a process within it, as much a part of its ongoing history as the filaments and voids and the accelerating expansion. The expansion that is slowly pulling the cosmic web apart is the same expansion that has been operating since the first second, and that produced, through the density fluctuations it amplified, the stars that built your atoms. Everything is connected through the physics. The boundary between you and the universe is a useful abstraction, but not an ultimate reality. Now consider what it means that we are living at this particular moment in cosmic history. The universe is approximately 13.8 billion years old. The first generation of stars formed within a few 100 million years of the Big Bang and burned through their nuclear fuel in millions of years, scattering heavy elements into space for the first time. Subsequent generations of stars formed from this enriched material, and the process of elemental enrichment continued with each stellar cycle, producing the chemical diversity that makes complex chemistry and therefore life possible. The Sun is a third-generation star, formed from material that has been through multiple stellar cycles, which is why it contains the full complement of heavy elements needed to build rocky planets and biological chemistry. Life on Earth emerged approximately 3.8 billion years ago, roughly 10 billion years into the universe's history. Complex multicellular life appeared only in the last 540 million years. Conscious, technologically capable life has existed for a few 100,000 years at most. On the cosmic timeline, we are extraordinarily recent, and we exist at a moment that will not last. The moment when the cosmic web is still fully visible, when the universe still contains enough observable structure to make cosmology possible, when the evidence for the Big Bang is still accessible in the cosmic microwave background, when the expansion history is still legible in the distribution of distant galaxies. In 100 billion years, none of that evidence will be accessible to any observer in our local group. The universe will have hidden its own history. We are living in the era when the universe's autobiography can still be read. The evidence of its origins is present in the sky right now, waiting for instruments sensitive enough to receive it. The cosmic microwave background is cooling slowly and will eventually redshift beyond detectability. The distant galaxies are receding and will eventually pass beyond the horizon. The window for cosmology, the window in which an observer anywhere in the universe can look outward and see the large-scale structure and trace the expansion history and infer the early conditions, is not permanent. It is open now. We are, by accident of timing, among the first minds in the history of the universe to look through it. That timing feels significant without being able to say precisely why. There is no cosmic reason why consciousness should have arisen at the moment when the universe's evidence is most legible. There is no physical law that required intelligent life to emerge during the era of peak cosmic visibility. It is, within the framework of standard cosmology, a coincidence, but it is a coincidence that has produced this: a species of conscious matter, made of atoms forged in dead stars, living on a planet orbiting a living star, in an era when the light of the universe's history is still crossing the sky in every direction, building instruments to receive that light and minds to interpret what the instruments record and voices to share the interpretation with other minds, in the hope that the understanding will spread. That is what science is, not a collection of facts, not a method for producing technology. Science is the universe's attempt, through the minds it has produced, to understand itself before the evidence disappears. It is an act of cosmic memory, preserving in human knowledge and human institutions and human records the history that the expanding universe is slowly erasing from the sky. In a very literal sense, every cosmological observation ever made is an act of preservation, taking information that exists in light and converting it into understanding that can persist beyond the lifetime of the light itself. The James Webb Space Telescope, looking back through more than 13 billion years of cosmic history at the first galaxies that formed after the Big Bang, is not merely a scientific instrument, it is a device for reading a story before it fades. The Sloan Digital Sky Survey, mapping millions of galaxies and tracing the cosmic web across hundreds of millions of light years, is not merely a database. It is a record of a universe in a particular moment of its evolution. A snapshot that will have no equivalent in the distant future because the subjects of the snapshot will have moved beyond the horizon. The physicists and astronomers who built these instruments and designed these surveys and analyzed the resulting data are not merely professionals pursuing careers. They are, whether they frame it this way or not, archivists of the cosmos, preserving what the universe knows about itself against the long thermodynamic future, in which that knowledge will become physically inaccessible. This framing is not intended to make science feel more heroic than it is. Most scientific work is painstaking and technical and proceeds in small incremental steps that feel anything but cosmic in the moment of their execution. The graduate student debugging a data reduction pipeline at 2 in the morning does not feel like a cosmic archivist. The referee reviewing a paper on baryon acoustic oscillations does not feel like a keeper of the universe's autobiography. But the cumulative effect of all those small technical steps across thousands of researchers across decades of work is the picture we now have of the universe at 1 billion light years. A picture that is, by any measure, one of the greatest achievements of any mind that has ever existed. And that picture tells us something that we should sit with rather than move past too quickly. It tells us that the universe had a beginning. It tells us that the beginning was smooth and hot, and nearly uniform, and that the slight non-uniformity in that beginning seeded everything that followed. It tells us that the universe is currently dominated by substances, dark matter and dark energy, whose fundamental nature we do not understand. It tells us that the expansion of the universe is accelerating and that this acceleration will eventually isolate every gravitationally bound island of matter from every other. It tells us that the universe had a specific history, a sequence of events that can be traced from the first second to the present, and that this history is written in light that is crossing the sky right now. It also tells us something about our position in that history. We are late arrivals. We came after the first stars and after the second stars, and after the formation of the solar system and after the emergence of life, and after the emergence of complex life, and after the emergence of consciousness, and after the emergence of language, and after the emergence of science. We arrived, in cosmic terms, just in time to see what is there to be seen, with instruments just sensitive enough to read the evidence that the expanding universe has not yet erased. We are, from the perspective of cosmic time, the briefest of visitors. And we have, in the time available, learned an extraordinary amount about where we are and how we got here. What we do with that knowledge is, of course, a human question rather than a cosmic one. The universe will continue its expansion regardless of whether any mind preserves what the evidence shows. The filaments will continue to grow, and the voids will continue to expand, and the dark energy will continue its patient work of separating everything from everything else, with complete indifference to whether any conscious process has noted what is happening. The universe does not need to be understood to continue existing. It does not need observers to proceed with its physics. It did not require anyone to witness the first 380,000 years of its existence, when it was too hot and dense for light to travel freely, and no eye, biological or technological, could have seen into it. The universe proceeds on its own terms. But we are here. And we are curious. And in the span of a few hundred years of serious looking, we have traced the history of a universe 14 billion years old to its beginnings and mapped its structure to distances of billions of light years, and identified the substances that dominate its energy content and measured the rate at which it is tearing itself apart. We have done all of this from a single small planet, using instruments built by the same evolutionary process that built the eye and the hand and the social brain. We have done it in what is, by cosmic standards, an instant. That instant is still happening. The next observation is being planned right now in some laboratory or observatory or theoretical physics department on the same small planet that produced every human being who has ever lived. The next measurement that will sharpen the picture, refine the numbers, resolve the Hubble tension, or deepen the mystery is being designed right now by someone who got into this work because they looked up at the sky as a child and felt something that they could not name, but could not ignore. That unnamed feeling is the beginning of every cosmological investigation that has ever produced a result. It is the origin of the journey we have just taken together. 1 billion light years from Earth, the universe is still the universe. The same physics, the same expansion, the same dark energy and dark matter, and ordinary matter, in their measured proportions, the same web of filaments and voids stretching in every direction to the limits of the observable. And at one small location within that web, on one small planet orbiting one ordinary star, a species of conscious matter continues to look outward and measure and theorize and argue and revise and look again. The light from that planet is in transit. It will take 1 billion years to arrive at the position we have been imagining. But the looking that produced the understanding you now carry happened here, in this moment, on this world, and the understanding itself travels at the speed of thought, which has no speed limit at all. The universe does not know that you understand it, but you do, and that across 1 billion light-years of accelerating darkness and ancient light and slowly dissolving architecture is the most extraordinary fact in the known cosmos,